Good afternoon, all of the students. I hope all of you are doing well in this lockdown phase 5.0, or shall I say unlock phase 1.0, whatever it is. The school and colleges are still remaining closed, so we need to continue our online teaching and learning session. So, in order to continue the session, we need to study the automata theory that I have been discussing throughout the semester. In the class, I have taken up to the finite automata part, and then I started discussing the push down automata Turing machine, and today I am going to cover the Turing machine. I have also covered miscellaneous topics from the finite automata that I didn't cover during the classes. So today we are coming to end of the session of this total online procedure. So I hope this video will help you to study and learn about the Turing machine. So let's start today's lecture. Okay, so today we are going to discuss about the Turing machine. Uh, all about the Turing machine we will try to cover up. Means whatever is inside your syllabus, we will try to cover up in this lecture. So we are going to cover up the introduction part, the definition part, and so we'll look at some of the examples. So the features that Turing machine have, we are also going to see the language that Turing machine can accept, and finally we'll look at the conclusion. Okay, so let's begin. Okay, so now let's discuss about the introduction of Turing machine. So before going on to the introduction of Turing machine, let's revisit the Chomsky hierarchy. So this was the Chomsky hierarchy. At the very root level or basic level, we have finite state machine, that means finite automata, and regular language and regular grammars. Okay. Then we had the push down automata and context free language, context free grammars. Then we actually had the lower bound linear bounded automata, right? And the context sensitive grammar, and finally at the top end we have the Turing machine. Actually, Turing machine, whatever it accepts, is called a recursively enumerable language. Why is it called like that? We'll see in our uh, whenever we go into the deep discussion about the Turing machine and the accepted language. But let's first of all we'll try to introduce the Turing machine. But before that, whatever we have seen so far is finite automata. In finite automata, we have seen that the memory was only the input string. That means there is a set of input string given, and you can only operate on that. Okay, you can either go from one state to another state using the input string, and that's all about it. Whenever we came to the push down automata, we saw that there is a input string, also a stack that is using as a memory to store the location, to hold the uh, state, not state, the input string that is being used, and different features of that. That means if the count of the input string it can hold, or the or number of occurrence of the input string it can hold. So that was the advantage of push down automata. But whenever we are coming to the Turing machine, it's a different concept altogether, right? It only has one data structure, that is a tape. Okay. Now, what is a tape? Tape is basically a linear data structure, you can say, which is containing all of the input strings. It is going to have a tape head which is going to point out at the current input, and it is actually an infinite string. Infinite data structure. It can hold infinite amount of data, but whenever we are coming to an end of a input string, after that the total cells will not be empty. They will be filled with a special symbol that is called the blank symbol. Okay, so what is a blank symbol? Blank symbol is basically denoted using that icon that is look like the space bar, right, in your keyboard. But you have to remember that this particular blank symbol doesn't belong to the tape alphabets or the input string. Okay, It doesn't belong to the sigma. Now remember always that this blank symbol and the null or phi is actually not the same thing. Okay, the blank symbol is just going to capture the um, total tape wherever it is not requiring that particular memory, so it is going to be filled with that blank symbol. But what is the difference with blank symbol with the epsilon, or let's say phi, the null? What is the difference? The only difference is the null or phi, it can belong to the input string, but the blank symbol will never belong to the set of alphabet or set of input strings. Okay. Now, what is the configuration? Now configuration is whatever I have said, that there will be input string. Let's say from here to here we have input string, and the rest of it is just blank. So that will be filled with blank symbol. Okay. So what are the operations that can be done? So there are four operations. You can read, you can write, you can move the tape head, that is pointing to the current alphabet. You can move it left or right. That means you can go either forward or backward. Okay. So to carry on the introduction part, there is an control portion. Okay, in this Turing machine. So the control portion of the program is similar to the finite state machine or push down automata, and it is a deterministic. Okay. So that control portion is going to hold that the tape head. Okay, so that means the tape head and control portion is going to be dependent on each other. That means based on one thing we are going to deduce another. So just let me just let me just clarify things up, that the control portion, you can say that this is basically where we are going to draw the transition diagram or transition table that we did for finite automata or push down automata. Okay, and already we know what is determinism, so control portion is always going to be deterministic in Turing machine. Obviously they are going to be non-deterministic Turing machine, but we'll come to that later. Okay. So there are some rules that we need to follow for Turing machine. As I said, we can read, write, and move ahead or move backwards. That means we can either move left or either can move right. But there are some rules that whenever a tape head is pointing to a particular location, you can only read or write that particular location. Okay, you can only read or write that particular location, and you can at once you can go one cell left or right. That means you cannot go jump into another cell straight ahead. You can just go one and one and one, like this. Okay. And what other thing we need to remember, this portion is actually belongs to the control portion. Okay, so in the control portion, we are, as I said, that we need to draw the transition diagram, and how we need to draw. So there will be two states will be there, and the transition is going to happen in this format where A implies B, comma R. Now A is the symbol to read, B is the symbol to write, and R is the direction. So if you are moving in the right direction, you have to place capital R. If you are moving in the left direction, you need to place capital L. If you want to replace something with something, let's say you need to replace A with B, so you need to write A implies B, and let's say you need to move it to the left side, so you can write A implies B L. If you only read the particular thing, you can just write A implies A and L. Okay, so in that way you can just move one direction to the left and you just write that you want to read, so there is no change basically. Okay, what are the rules apart from this? That the rules say that there will be um, as I said, control portion is basically like the finite automata. Okay, apart from that, there will be initial state, there will be final state. Now here there can be two states. Okay, one is an accepted state, another is rejected state. Now in final state finite automata or push down automata, I have seen that if it accepts, it accepts. So there is nothing like an accepted state or rejected state. There was only a final state and an initial state. The language either gets accepted by the final state or it doesn't get accepted by the final state. So if it doesn't get accepted by the final state, that doesn't mean that it is going to produce another final state that is going to be called reject state. But in case of Turing machine, this is going to happen. Okay, so there is going to be an accepted state and another reject state. And the computation can happen in three ways. There are three ways in Turing machine. So you either halt and accept, or halt and reject, or you can just fail to halt. In that case, it is called a loop. So the machine goes into infinite loop. It cannot halt. So it is just writing over and over again something. So let's just take an example for any C program. You just write for, and you don't give any condition, so this becomes an infinite loop. Okay, and you are saying that print a equals to b. Okay, so for infinite times it is going to be written. Okay, so it is unable to halt that particular thing, so it is going into a loop. Okay, so these are the basic introduction for the Turing machine. Okay, so now we are going to look at the formal definition of Turing machine. Turing machine is a automata that consists of seven tuples. Q is the set of non-empty states. That means the set of states like push-down automata, finite automata. Sigma is the non-empty set of symbols. That means it is going to hold the uh, input alphabets. Non-empty set of tape symbols is tau, that you have already seen. The tau, that means the still tape symbol means it it moves to right or left, that is going to be inside this. Delta is the transition function. Okay, so this transition function, how it is going to work? So you are going to have a particular state and you are going to have a particular symbol. Upon applying that particular symbol on that state, we can move to right or left on the tape symbol. That means whatever tape is currently locating at. Okay, so um, and the new state, that will be q. Okay, so if I want to look at this thing, you can see that here is an example given, that you are applying an input symbol of A on the state Q1. It is going on to another new state, that is Q1. From Q0 to Q1 it is going. Y is the tape symbol and R is the transition. Okay, so tape symbol, basically you can say that this is the output, that what is happening or what it is producing. So that is going to be written inside the tape, so that is called a tape symbol. Okay, so obviously it is going to have initial state, blank symbol, and set of final state that we have already discussed. Now, during thesis, we need to know about this also, that it states that any computation can be carried out by mechanical means, can be performed by some Turing machine. So obviously, whenever you are talking about any computation that can be done using any computer, that is basically can be done using a Turing machine. Take any computer programming language and you can check the acceptance or rejection or going into loop using a Turing machine. Anything that can be done on an existing digital computer can be done using a Turing machine. Okay, and no one has been able to yet suggest a problem solvable by what we consider an algorithm for which Turing machine program cannot be written. Okay, that means you can take any language in any computer programming language, and you'll be able to find a way to write the Turing machine program of it. Okay, it is not impossible to write it. Okay, there hasn't been any algorithm or any program that cannot be solved by the Turing machine or cannot be written in Turing machine. And we have already discussed that Turing machine, the language accepted by Turing machine is called a recursively enumerable language. Okay, so recursively enumerable language is the language that is accepted by the Turing machine. Okay, let's take an example of Turing machine. So the first problem given is design a Turing machine that recognizes the language L equals to 0, 1, star 0. Okay. So that means, what is this means? That means it should have a 0, then it can have any number of 1. So 1 star means the closure of 1. Okay, so there can be any number of 1, and at the end there will be a star, sorry, a 0. Okay. So if I want to draw the Turing machine, this is how it look like. Okay. So now you can go and outlets that why I have just drawn it all together and why I didn't discuss it step by step. Obviously, you can. I mean, you can under. I am going to let you help to understand that how this thing is going to work. Okay. So let me just carry on. I'll not go to this transition diagram because let me just go to and take a string and then let me explain it. So let me just take this particular string of 0110. Okay. So as it accepts 01 star 0, so it will be able to accept anything. Okay. It will be able to recognize anything that is going to help it. Uh, so how can you uh, do this using a Turing machine? How can you enforce it? Now, if you look at this, it is basically a uh, efficient finite state machine. Okay, you don't need to harness the power of the Turing machine totally. It is just we need to look at the particular tape and we'll see that how this movement is going to work. Let me just draw the tape at first. Okay, so at the beginning we have this initial state of A. We have 0 and 1 as accepted symbols or input alphabets, and we also have the space blank symbol. Okay, so first of all we are at A. Now we are checking for this 0110. Okay, so uh, first of all I will apply 0 on A. So what I am going to get, I am going to get the small x. Okay, next I am going to apply another one, and I am staying at B, and I am going to produce a Y. Next again I am applying 1, so I am going to produce another Y. Now if you look closely, this particular thing is going to work on 0110, 01110, 0. You can put any number of 1 and it is going to produce self loop over and over again. So it is not never going to the rejected state from here. It will only go to the accepted state. Okay, we'll see how. So let me just carry on this with this. Next we'll put 0 on this particular state and we're going to go to the C state. Okay, so here I am going to get another x. Now on C state I am going to, if there is nothing, that means there is a blank symbol over here. So if this is a blank symbol, it is going to the accepted state. Okay, so this is a blank symbol and everything here will from now on will be a blank symbol. Okay, so that is how it is going to work. So it doesn't matter that how many number of one you put there, it is always going to be accepted because those one will get accepted. Okay, so if there was a string like 0 1 1 0 0, what would have happened? Now in that case it would have come to 0 for here, then 1 for here, then 1 for here, then 0 for here, and finally when it is getting another 0 for this one, it will go to the rejected state. Okay, so it is only going to be accepted when there are plenty of number of ones. It can be 1 1 or it can be no one. Okay, even if this is closer means it can be an epsilon, right? So in that case it is going to be double zero. So if it is a double zero, it is going to come here, it is straightly going to the C state and it is going to be accepted. Okay, so I hope this was clear to you. Now we told that this is the control center or control portion of the Turing machine. Now, and we also said that it is deterministic. So if it is deterministic, that does mean that each of the state is going to produce different, or say, each of the state is going to have a transition for every symbol. So what are the symbols we have? 0 1 and blank. Okay, so let's see. For A, there is, for 0 there is transition, for 1 there is transition, for blank there is a transition. For B, there is, for 0 there is, for 1 and there is for blank. For C also we have a transition for blank, 0 and 1. So that means the control portion does have all of the things that we have promised. Okay, so that is how it has been designed. Okay, so now this is a little bit complex problem where we will try to design a Turing machine that is going to recognize 0 to the power 1 in 1 to the power n. Now this we have already seen in our CFG, okay, or push down automator you can say. So now we'll look at this, but before that we need to first of all understand that how we are going to work on this. Okay, so let's see this algorithm that change 0 to x. So wherever I have 0, I have changed it to x. Move right to the first one. So I am searching for the first one. This is my first one. Change it to y. Move left to the leftmost 0. Now the leftmost 0 is this one. So I replace this with another x. Repeat the state until no more 0. Make sure there is no more 1 remain. Okay. So you just cross this x, and cross this, and y. This is how it is going to work. Now if I want to design a Turing machine, it will look like this. Now for at first glance you will see that there is no reject state. Is that so? No, that is not the case. There is the reject state, but just that it is not written over here. So where is the reject state? Let me just look at the Turing machine closely. So as I said in the previous slide that Turing machine is always deterministic. Okay, so that means for each of the inputs and each of the symbols, we are going to have a transition. So let me just look at this A state first. Okay, so A, so what are the input symbols we have? 0 1 x and y, right? So for A I have 0, for y, and obviously there is for x also. Okay, so what I don't have is for 1. Okay, so uh, where is that one? So that one is actually in the reject state. So if I get a 1, it will go to the reject state. Okay, straightly. And also we have for one transition for blank symbol. Okay, okay, so that is the main or basic uh, fund of this thing, that reject is there, but I just haven't visualized it or shown it yet. So why this will go to the registered? Because for this particular example you need to produce 0011 or 01 or even 0011 like this. But if there is a 1 at the beginning, then it is at all not going to be accepted because the input string will fail in that case. Okay, so that is the reason. Okay, now, so how this is going to work? So first of all, I have to apply, uh, I have to replace this 0 with an x and move right. Upon moving right, there is a 0, so I read it. There is another 0, I read it. There is another 0, I read it. I reach here. Then I have another 1, so I will replace it y and move to left. Okay, so after moving left, I have another 0, so move left. I have another 0, move left. I have another 0, move left. Upon moving left, I will see that there is an x. So if there is an x, I will move again in the right direction and I'll just read it. After reading it, I will see that there is a 0 on, now I am in A state. Okay, this one. After reading that there is a 0, I will replace it with x. Again, I will read that there is a 0, 0. There is a y also. For y, this is, I just have to read it. Okay, and then I will find that there is 1, so I will replace it y, and then again I will just uh, use these two to move back to here. I'll cross this one, then come to here, cross this one, come back here, cross this one, and come back here, cross this one. Now whenever I have crossed this one, where I am currently, so I have replaced with y, and currently I am in C state. Okay, so now again I have to look at this thing. So if I am reading that y, move left, move left, move left, then again I am reading that there is x. There is only, so upon after reaching that state, that I am seeing that there is x. Okay, so now I am here in the A state. So after reaching the A state, now I am moving to right again, y, 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 in this direction. Reached here. Now whenever I have reached here, I am in D state currently. Now after reaching here in this state, when the tape is it is here. Now if there is a blank symbol, I'll just accept it. Okay, I'll just accept it from here. So that is the total thing solved. Okay. Okay. So now we are going to discuss about the charge Turing thesis. Before going on to the charge Turing thesis, let me just give you a brief history behind this. So basically, there is a person called Alonzo Charge, and there is a person called Alan Turing. Now you already know about the Alan Turing, who was the inventor of this Turing machine that we have been discussing so far. But this Alonzo Charge actually introduced the lambda calculus thesis theory that we have used in mathematics. So, according to both of them, that means Alonzo Charge and Alan Turing. Alonzo Charge, according to Alonzo Charge, that lambda calculus is whatever is accepted by lambda calculus or programmable by lambda calculus is will be said computable. But Alan Turing, after the invention of this Turing machine, he said that if anything is accepted by the Turing machine, that means it is computable. Okay, so now after this, then came this particular Charles Turing thesis, which says that Turing machine and lambda calculus are equivalent in power, but in general terms we always have been using Turing machine. Okay, so that means if we want to test any program or computer program or any algorithm, we use the Turing machine, but this lambda calculus is equally accepted for that. So we both came to an agreement that Turing machine and lambda calculus are equivalent in power. And algorithmically computable means computable in Turing machine. It also means it is computable by lambda calculus, but we use the Turing machine more than this thing. Okay. Now, what are the other variation of Turing machine? So, other variation of Turing machine may have these features, that one tape or many tape. That means it can have one tape or many tapes. So far, we have seen in all of the examples and discussion that it has one tape which is accepting the strings, but it can have more than one tape. Okay. Infinite on both ends. So we have seen mainly that the tapes are basically infinite on the right end, but it is possible that it will be infinite on the left end also. We are inserting things from the right end. Alphabets only 0, 1 or more. Yeah, obviously it can be anything else apart from 0 or 1. Can the head also stay in the same place? This is also another question that we have seen that the tape head, here head means the tape head has been moving from either left or right, but is it possible to stay in the head in the same place or not? And allow non-determinism. Is it possible to build up a non-deterministic Turing machine or not? So all of this will lead to one answer, that all variations equivalent computing capability. That means all variations are equivalent. So even if the tape has many, even if a Turing machine has many tapes or has infinite in both ends, or can accept other alphabets than 0 or 1, or has a tape head that stays in the same place or allows the determinism, still it will be called a Turing machine, and still it will be equivalent to the existing Turing machine that we have seen. So that's why all of the algorithms or computer programs that is invented will be accepted by the Turing machine. I have said this previously, that there is no program or no mathematics or nothing that cannot be computed using a Turing machine or programmed using a Turing machine. Everything is possible to be programmed using the Turing machine. Now talking about the this machine charge Turing thesis, we need to also clear up one thing, that we have plenty of times we have heard the term Turing test. Okay, but Turing test and Turing machine are not the same thing. Turing machine is whatever we have seen in so far, but Turing test is completely different. It is related to artificial intelligence. Turing test is a test which allows you to test the skill of the computer if the device or the particular computer is as intelligent or as human or not. That is totally different. But both were built up by Alan Turing. That's why he gave the name of Turing machine and Turing test, but both are completely different. Okay. Now let's talk about different classes of languages. So far we have seen regular language CFL, but there are two types of language in Turing machine that can be seen. One is decipherable, another is Turing recognizable. Now what is the difference? Now we have talked about the Turing machine and their uh, final state. In the final state we have seen that it can be accepted and hold, rejected and hold, or loop. These three are the possibility. So this is the main difference between these two. So in decidable, if a string is accepted by the Turing machine, it will hold. If it is rejected by the Turing machine, if we pass a string such that it doesn't belong to or will not get accepted by the Turing machine, it will reject it and hold. That will be for this decidable Turing machine. Sorry, decidable language. But Turing recognizable language is something different. In this case, if we pass a string that will be accepted by the Turing machine, then it will get accepted. So in that case, it will be called Turing recognizable. But if you pass a string that is not that will not get accepted by the Turing machine, in that case, it will not reject and hold. Instead, it will go into an infinite loop. It will not stop. So that's why it is called a recursively enumerable language. Turing recognizable language. So that is the main difference between these two. Okay, let's talk about non-determinism in Turing machine. So Turing machine can be non-deterministic, and the concept of non-determinism is same as whatever we have discussed in full-term automata and finite automata. That means one state upon getting one particular input alphabet or input symbol, it can go to multiple states. Then it can produce multiple transition. Okay, so here you can see that the transition function will get a little bit changed. Here we can see that there will be a set of transition. So let's take an example. So let's say that for deterministic, it is going from Q to S upon getting uh, this transition. B implies C, and it is moving right. That means whenever you will get a B inside the tape, you replace it with a C and move to the right. But here during the non-deterministic, there are three possibilities. If you encounter with an input alphabet of B, you can replace it with a C and move to right and go to state T. You can replace it with A and move to left and go to P step, or you can replace it with C and go to left and go to A step. So that is non-determinism in Turing machine. Now the configuration of Turing machine, non-determinism. Actually, it is acceptable for determinism and non-determinism, but let's just look at this particular thing. That this configuration says that a way to represent the entire state of a Turing machine now at a moment of computation. It captures the current state, captures the current position of the head and entire tape contents. So you can use one particular symbol to represent that where the tape head is currently at and what is the next possible move that is going to happen. Okay, so let's take an example that here this particular string is given ABB ABAB okay, and the tape it is currently pointing at this fourth box on B. So here I am just writing, instead of using the tape head, I am using a particular symbol, let's say Q. Okay, so Q is on the fourth place and it is directly pointing at the this particular B. This B is actually this B. Okay. And whatever the transition is going to happen after that, we will just apply that transition whenever it happens. So this is one example of this application of this thing. Okay. So let's take this example. Obviously, this is not a complete transition diagram. It is just a part of a diagram. So let's take that Q, S, and P. There are three states in this portion of the transition diagram, where upon getting A input alphabet, it will replace it with X and go right and go to A state. Upon getting B alphabet, it will replace it with Z and go to left. And for S, if it gets a B input alphabet, it will replace it with small y, go right and go to P state. Okay, so let's say that we have a string of C C A B B C now, and let's say that it is currently pointing at this particular position of the letterhead is currently here. Okay, so how can I write this? So I can write this like this: C C, like I have done over here. So I just write C C capital Q A B B C, and this Q is pointing towards this. Now next what we need to apply is A on this thing. So currently it is in Q state, we are applying A. So A will be replaced with X and we will move right. Okay, so C C X. Now we are in the S state, we have moved right, and now we will be looking at the next alphabet, that is B. Okay, and Upon getting B, we will replace it with Y and move right. So I will write C, C, X, Y, and we'll move to P state, B, C, and it is looking at the right side. This is how it is going to happen. Okay. So that is how it has been shown in the diagram too. Okay. That is how to write it. Now, if it was a non-deterministic Turing machine, how would have written? How you would have written it? Let's take this example. Okay. So here you can see that this is also part of a diagram where this Q state is going to P and going to S on getting a symbol. It is replacing it with X or Y, moving right or left. So obviously this is non-deterministic. Okay, so let's say we have that same particular thing, C C A B B C, C C A B D C. Now let's say that uh, it is pointing to this particular position. Okay, so here I will write it as C C Q A B B C, and Q is pointing towards A. Now using the A, there can be two transition possible. Either it will replace with X and move right, or it will replace the A with Y and move left. So either I can go right. So there are two transition possible. If I move right, then I will write it C C. If I move right, I have to replace it with X. C C X. The state I am going to is P B B C, and P is pointing towards this P. Or I can have another step, another transition that is going to the left and going to S. So if I go to left, I have to replace that particular A with Y. So this A will be replaced with Y. So I have to write C C C Y B B C. Okay. Now as I was initially here, I have replaced this Y and I have to move to right. So I will go over here. Okay. So that is what I have shown over here. Okay. So that is how it is going to happen. So what are the possible outcomes? Same as the deterministic Turing machine, that I can either accept it. That means Turing means the machine can accept it, or halt and reject it, or it can go into an infinite loop. That means it is continuing the computation, but it is never reaching the accepted state. That is why it is going over and over again for infinite amount of time. So decidability and undecipability, we have talked about little bit of this in our previous slides, but let's get a clear picture about what is decidable and what is undecidable. So decidable means you can either accept or reject it. So there is going to be a particular outcome of everything. Either it is getting an acceptance or getting rejection. So that is decidable. And undecidable is recursively enumerable language. That means if it is not decided or not accepted rather, it may go to an infinite loop. Okay. So here we are saying that language will is said to be recursively enumerable language if there is existing a reading machine that will accept for all input string which are L. So L is the particular language. So it is getting accepted, no problem, it will accept and hold. But if it doesn't accept, what will happen? It may or may not hold for all input string which are not in L. So there are three types of further we can break it into three types. That is, one is recitable. Obviously, we have talked about this. That is the recursive language. Partially recitable language. So this is the case where it is a recursively enumerable language, but it may get altered. Okay, so that is partially decidable, and undecidable means the language is undecidable if it is not decidable. So that is the case where it is getting either accepted or going into loop. So you don't know if it has gone to loop, you will never know that whether it has gone rejected or anything, because whenever you go into an infinite loop of a computer program, you will never know that uh, why it is acting so weird, uh, unless you stop the program and then go back into the coding part of it. Okay, that is undecidable. Partially decidable means whenever you are running a program, it is giving an error. So in that case, it is saying that I am rejecting whatever you have written, but I am also stopping the program from running. So there you can go back and change the thing. Okay, so you can work on your failures. So that is partially decidable, but it doesn't happen always. In some cases, it is going to happen. Okay. So this is the table given about recursive language, and Turing machine will always halt. For recursively enumerable language, Turing will halt sometimes and may not halt sometimes. So it may halt sometimes. In what cases? For partially decidable language. So for example, let's say that there is a program running and there is something in C program. We have seen that if there is a um, logical error, or let's say divided by zero error, but still it is in an infinite loop. It is going into an infinite loop. But in Java, we have seen that if it has a logical error of division by zero, then it is going to show the exception instead of going into the first of all going into the mm, infinite loop and then throwing out the exception. No, so that is where it will halt. In spite of getting into an infinite loop, it will halt. Decidable language is recursive language. Partially decidable language also belongs to the category of recursible and variable. Undecidable, there is no Turing machine for that language. If it is undecidable, you cannot. It means you cannot understand if it has gone on to the infinite loop. It is as simple as that. Okay. Okay. So let's talk about the halting problem. So what is the halting problem? The halting problem is basically is a question that is it possible to build up a Turing machine for which it will be possible to never go into infinite loop or something like that. This is a halting problem. That means a halting problem basically means that under that condition it is never going to a halt. If it is belongs to that particular language, or it doesn't gets accepted by the particular language, it should always halt. But that's not the case we have seen so far. Sometime it may halt, sometime it doesn't halt. So let's look at the question that given a program, will it halt? Uh, and given a Turing machine, will it halt when run or some particular given input string? Given some program written in some Java, will it ever get into an infinite loop, or will it always terminate? So based on this question, let's ask this next question that accept all valid Java. Is it possible to build a machine that accepts all Java codes and never goes into an infinite loop? Now this has two parts. One is accept all valid Java codes. Yes, it is possible to build up a Turing machine like that. But never goes into infinite loop? No, it is not possible. It is never possible because if you don't enter the infinite loop, you'll never know. And once you enter the infinite loop, you'll never come out. So that is a backbone of the halting problem. Now the answer to these three questions are given here. Given a program, will it halt? In general, we cannot always know. It is not possible to know. Given a Turing machine, will it halt when run on some particular given string? The best we can do is run the program and see whether it halts or not. So it is just test and fail method. Okay. So it is not a conclusion, rather than it is a test and training method, or testing training validation method. You can say, given some program written in some language, will it ever get into an infinite loop, or will it always terminate? So we have seen that for many programs it will always halt. Sometimes it may goes into infinite loop. So it totally depends on that, whether it goes into the infinite loop or not. We never know. We just have to test it. And in general, we cannot always know. So using these three questions and from three answers, so you can conclude that for programs in general, the question is undecidable. That means the halting problem is undecidable. So if it is undecidable, it belongs to the recursively enumerable language. Okay, and if it is undecidable, there is no Turing machine that can be built to accept the halting problem. So it is not possible to solve. Now let's quickly separate the universal Turing machine. So universal Turing machine is basically one kind of Turing machine that is basically a simulator of the actual Turing machine. So let's just take this example, that there is a Turing machine M that accepts the language W. Okay. So is Turing recognizable? Obviously it is. Given the description of a TM, so let's say that this A suffix TM is the Turing machine, and some input can determine whether the machine is accepted. So the solution is to simulate and run the Turing machine on the input. So universal Turing, let's say it is uh, UTM. Okay. So what it is going to do? It is going to take this same string W, and it is going to either halt, accept and halt, or reject and halt, or will not halt and go into the infinite loop. Okay. So now what is the concept behind this? That you have the M or A suffix TM, the actual Turing machine, and here you have the universal Turing machine that can emulate the whatever this thing was capable of, but this thing is busy doing other work, and the description of it is already passed on to the description and information about it has been already passed on to the universal Turing machine. So it will try to act like this A suffix TM. It will either accept and hold, or reject and hold, or just will not hold. So it is recognizable but not decidable. Okay. So what are the things that was going to be needed in this UTM? The description of the Turing machine, that is the description of A suffix TM, the input string, obviously we need to pass on to the input string, or what's the point of all of this. What it will do, it is just going to simulate or act like this particular M, this Turing machine, and behave just like M, may accept or reject a loop. Now there is a big difference. Okay, this particular thing, I have said that M is a Turing machine that accepts W. That means it either accepts or rejects the W, but it will never throw this W into an infinite loop. Okay, but universal Turing machine, if it is accepted, then it is accepted. If it is not accepted, it can either halt and reject, or it will not halt at all. That's a universal Turing machine is a recognizer. It is not a decidable Turing machine. So UTM is a recognizer. It is basically an emulator for the original Turing machine. So you can take as an example that whenever you are programming let's say you are writing a C program where you are trying to build up a calculator. or let's say you are writing a program that can add, subtract, multiply, and divide. So there actually what you are trying to do is you are writing a code so that you can calculate anything. So you are basically building up an emulator of the calculator, right? You can think it like that way. So in that case, it will tell you that whether 1 plus 2 is 3 or not, 1 into 2, what is the value. But will it be possible to tell the exact value of, let's say, 1 into pi? If you pass pi over there, will you be able to accept it? No. Then again you have to write in a different code. Even if you write it in a different code, will it be solve everything that is possible by the calculator? Because calculator itself is a different device and it has multiple functionality. Obviously computer is much more uh, functional device than calculator, but you get that it is actually emulating the calculator, not the calculator itself. So if you get an error on the calculator, it will show an error. You can just press the on or C button. But if any of the case your program crashes, can you still run the program? No, you just have to stop the program and then you again have to rerun it. Okay, so that is basically the concept, that you can either accept or reject it, but you don't put the program into infinite loop whenever you are using the actual device. But whenever you are using an emulator or simulator, in that case, either it will get accepted or it will may get rejected or may go into a infinite loop. So that is basically a recognizer, not a decide. Okay, so that comes to with that we come to an end of the syllabus for this term. Turing Machine was the last module, and I have already covered all of the miscellaneous topics from your module 4 in this particular slide or particular lecture. So I hope all of you have learned the automata theory well during my class and in this online session. I hope to see you all very soon whenever this lockdown gets completely uplifted for the college and universities also. Till then, stay safe, stay at home. Please take care of yourself and your parents and whoever is in your family. And remember, teaching and learning is a process that should never stop, because it is like eating, feeding, everything like that. If you stop this teaching and learning process once in your life, your system will fail. That's the main thing behind it. And with that, I would like to conclude my class. If there is any bits and pieces left from any of the topics, I'll try to cover up with notes and PPTs and several audio lectures or maybe supplements. I will use the EduCampus app, WhatsApp group to share the notes. But this is 31st minute, so I'm just ending our course and curriculum. So I hope you will do well in your exam, if it is organized at all in this semester. If it is not, I hope I have taught you well. Please give your feedback regarding the videos in the group or in the app. Thank you. See you very soon. Bye.